In this video, we have the definition, examples, and a few results on permutation groups. A permutation is a one-to-one mapping of a set S onto itself. Now, the set of all permutations on S, denoted by A of S, forms a group called the permutation group of S under composition of mappings. The reason is the composition of bijective mapping is bijective, the composition of mapping is associative, the identity mapping is always bijective, and the inverse of a bijective mapping is bijective. Now we have these few remarks. The term permutation is used mainly for a finite set S. In that case, if S denotes this, then we denote a permutation sigma on S as this two-row notation. In the first row, we have the elements of S and the corresponding images in the second row. So this we can read as sigma takes 1 to I1, or we can also say that the image of 1 under sigma is I1. Similarly, sigma takes 2 to I2, or we can say that I2 is the image of 2 under sigma, and so on. Now the set of all permutations on this finite set S is a group under composition of mapping, and this is called the permutation group of degree n, or the symmetric group of degree n. When S is not a finite set, we consider the collection and call it as A of S. There also it is called permutation group or symmetric group, but we attach this of degree n when we have S consisting of n number of elements. Now the order, how many elements that we can have in Sn, it is n factorial, for the reason that if sigma is a member of Sn, then sigma has n choices to send 1 to the elements 1, 2, and so on n. And because sigma is 1 to 1, when one of them is fixed, then you have the remaining n minus 1 choices only. So since sigma is 1 to 1, sigma has n minus 1 choices to send 2 to 2 and so on up to n. So if we proceed like this, we see that sigma has n into n minus 1 and so on up to n, that is n factorial choices to be in Sn. So the number of elements in Sn is n factorial. Now how this composition of two permutations that we can find. Now in S6, for example, suppose we consider the two permutations theta and phi given by this. Now theta composition phi is calculated in this way. 1 is taken to 2 and here 2 is taken to 3. So 1 is taken to 3. And we have 2 taken to 3. There 3 taken to 2. So you have 2 taken to 1. So when we consider the operation, when we consider the operation from left to right that we go. See, 1 is taken to 2 and here 2 is taken to 3. So that means your 1 is taken to 3. So that is what we have, 1 taken to 3. Similarly, 2 to 3 you have 2 is taken to 3 and here 3 is taken to 2. So that means you have this, your 2 being taken to 2. So like that, 3 to 4, here 4 to 6, so 3 to 6, 4 to 5, 5 to 5, so 4 to 5, 5 to 6, 6 to 4, so 5 to 4, 6 to 1, 6 to 1, and 1 to 1. So you have 6 being taken to 1. So that is how the composition of two permutations is calculated. Now to find the inverse of a permutation, that is theta inverse, then what is that we have? See, if we are given theta as this is our theta. We want to find the inverse of that permutation, namely theta inverse. So what we do is we just interchange the rows. So this 2, 3, 4, 5, 6, 1 that's written here, and the corresponding this row, first row, is written as the second row. But we usually write the first row entries in the ascending order. So when we consider that this 1, 2, 3, 4, 5, 6 we write The image of 1 under, the image of 1 is 6. So you have this, and under theta inverse. And the image of 2 under theta inverse is 1. So like that, in that order, we rewrite this and we have this. So just interchange the rows to get the inverse. And to find whether our calculation is correct or not, just multiply and see. Here is your theta. Theta 1 is taken to 2 and here 2 to 1. So you have 1 to 1. And theta is 2, under theta 2 is taken to 3. So you have this. And theta inverse 3 is taken to 2. So you have 2 to 3, 3 to 2, so 2 to 2. Similarly, 3 to 4, 4 to 3, 3 to 3, 4 to 5, 5 to 4, so 4 to 4, and 5 to 6, 6 to 5, so 5 to 5, and 6 to 1, and here 1 to 6, so you have 6 being taken to 6. So we have a theta inverse to be correct, and therefore just to get theta inverse, just interchange the rows. Next we have this result. Let S be a set and theta be an permutation. Then define for any two elements AB in S a relation tilde on S by A is related to B if and only if A is congruent to B with respect to theta. So the meaning of this is the B is the image of A under theta power I for some I in Z, that is for some integer I. So A is congruent to B with respect to theta. A is congruent to B with respect to theta. What is the meaning of this? B is the image of A under theta power I for some integer I. So now we establish that this tilde is an equivalence relation on S. So of course we have to check reflexivity, symmetry and transitivity. Now for reflexivity, every element should be related to itself. But we know that identity mapping takes any element to itself, and that identity mapping being bijective, it's a member of A of S, and that is denoted as theta raised to 0. So you have reflexivity to be obvious. And for symmetry, to take A to be related to B. That is, A is congruent to B with respect to theta, which means this B is the image of A under theta. So B is the image of A under some theta power I for some integer I. Now this is rewritten in this way. You are applying theta raised theta power I inverse, which is nothing but this. So you are applying that on both sides. So you have this. That in turn gives B is congruent to A with respect to theta. So you have B related to A. And here let A be related to B and B be related to C, which means A is congruent to B with respect to theta and B is congruent to C with respect to theta. B is congruent to C with respect to theta. So from the first one, what we have is B is the image of A under theta power I, and this one means C is the image of B under theta power j, where I and j are integers. So from here you replace your B by A, the image of A under theta power I. So that gives us this. I and j are integers. I plus j is some integer. Take it as say some L. So your C is now the image of A under theta power L, and therefore your A is related to C. That proves the transitivity. Next we have the definition of orbit. The equivalence class of S under theta. Where is S? S is in capital S. That is given by C. Once we have equivalence relation, we can talk about the equivalence class. Equivalence class for each and every member of capital S can be determined, and we have as a sample an element S in capital S, for which the orbit, that is the equivalence class of S under under theta, is given by this. So all those elements which are related to S, all those elements in S which are related to the small s. but x related to s is same as s related to x because of symmetry. And the meaning of this is this x is the image of s under theta power I for some integer I. So your x is this. So you have now the orbit of s and theta to be all those the images of s and theta power I for some integer z. So when we actually list out the elements, this is how they will be. The set consisting of s, the image of s under theta, image of s under theta square, and so on. So this equivalence class of s under theta is called the orbit of s under theta. Now we have this result. If s is finite and theta belongs to a of s, then for some k depending on theta, s, the image of s under theta power k is s itself. That means you can always have an integer k such that theta power k is the identity mapping. So to establish this, we consider this s is in s naturally. So let s be finite and theta belong to a of s. If s is in s, then we know that s theta square, and the image of s under all this will be in s. Now since s is finite, this cannot go on and on. We have to have integers I and j with say I greater than j, such that s, the image of s under theta power I to be equal to the image of s under theta power j. Now this is true for every s in s, so as the images are equal, the mappings must be equal. And this in turn gives theta raised to I minus j is identity mapping. So because this is true with mappings, when mappings are equal, the images must be equal. So we have this. So we have now we consider b to be the set of all positive integers such that the image of s under theta power L is s. Such collection is named as b. Now because I minus j belongs to this collection, this is non-empty. Whenever we have a non-empty subset of positive integers, by well-ordering principle, we can have one k in z plus the least positive integer, for which you have your s theta power k to be s. We can find one least positive integer k such that this one holds. So we have the image of s, the equivalence class of s under theta, or rather the orbit of s under theta to be s theta square, and so on, s theta power k minus 1. Because once you have theta power k, you will get back this s. So it varies for each and every theta. So for one theta, this k may be 3. For some other theta, it may be L. For some other, it may be 10. So like that, it varies. Now, by a cycle, next we have this definition. A cycle of theta of length k is nothing but this ordered set. See here with this flower braces that we have, we'll have to represent that as with this ordinary parenthesis. So that is called a cycle of theta. And a cycle of theta is ordered by this. Mostly we will write this without this comma also. So yes, s theta like this also. In some book they refer like this. In some books we have this. We will be following this notation. Even though in the definition it is given here like this, we will be using only this. Now a cycle of length 2 is called a transposition. For no other length we have any name, but cycle of length 2 is named as a transposition. Now a product of even number of transposition is called an even permutation. See, we have a permutation, say sigma. It is written as product of even number of transpositions. Something like this, say 1, 2, 1, 3. Then in that case, what we call the sigma is an even permutation. Suppose we have this to be, say, sigma to be product of 3 transpositions. In that case, we call that to be odd. So if we have only even number, we call that to be even permutation. If we have odd number of transpositions, then we call that to be an odd permutation. Now the length of a cycle is determined by the number of elements within the bracket. So how do we say that? It's a length 2 means you have only 2 elements. Suppose we have 1, 2, 3, 4. We have like this, say, then you have the length of this cycle to be 4 because there are 4 elements. So the length is determined by the number of elements written within the bracket. Now given 2 cycles, say this and this, 2 cycles are given. Then when do we say that these 2 cycles are disjoint? See here you have this 4 to be common to these 2. So you cannot call this one, that is theta. If theta is this and phi is this, you cannot call these 2 to be disjoint. But on the other hand, if we have sigma to be this transposition, or it can be even a cycle, then in that case you have these 2 permutations to be disjoint because you don't have any element common. So if you have like this, you cannot call them disjoint, whereas if you have like this, you don't have any element common to them. So in that case, you call them as disjoint cycles. If 2 cycles are disjoint, then whether you write theta composition sigma or sigma composition theta doesn't matter. Whereas here, if they have some common element, then you cannot write theta composition phi as phi composition theta. So when they are disjoint only, suppose I name this as phi, then theta composition phi is same as phi composition theta. Now every cycle is obviously a permutation, but every permutation need not be a cycle. See, we can see this and we can consider any example, even this example that we can consider any cycle. When we consider any cycle, say this, if we consider it is a permutation, because what is the meaning of this? We have 1, 2, 3, 4, 5 in this, if we are in S5, because otherwise we will not know how many elements to be written in the first row. So we'll consider this to be a member of S5. In this, the meaning of this is 4 is taken to 5 and 5 is taken to 4. The rest are taken to themselves. So every cycle is a permutation. And the same way, if this is in S5, then the meaning of that is you have 1, 2, 3, 4, 5. In that, only 5 is taken to itself. The rest, 1 is taken to 2, 2 to 3, 3 to 4, 4 to 1. So you have every cycle to be a permutation. But a permutation need not be a cycle. See, for example, if we consider this permutation, then in this we explain that how to write that as product of cycles. So you will have this to be 1, 2, 3, 4, 6, 5. Because 5 taken to itself, this is how it should be written. 4 is taken to 6, 6 is taken to 4, you have this. And here 1 is taken to 2, 2 to 3, 3 to 1, so 1, 2, 3. So this is a permutation, it's a product of cycles. So that is what is mentioned here. Every cycle is a permutation, but every permutation need not be a cycle. It can be a cycle. See, if we consider this permutation, this is a permutation in S5, which is given like this, 2, 3, 4, 5, 1. So in that case, then you have this to be a cycle. 1 taken to 2, taken to 3, taken to 4, 5 taken to 1. So in this case, it is a cycle only. So this permutation is a cycle, but in general, it is not that a permutation is a cycle. As in this case, we don't have that to be a cycle, but it is a product of disjoint cycles. Next remark is, given any a cycle like this, we can always write that cycle in this way. See, for example, suppose I consider this cycle 1, 2, 3, we can write in S3, we consider this, say, we can write this as 1, 2, 1, 3. This we can write as 1, 2, 1, 3. The reason is, when we consider 1, 2, the meaning of that is, this cycle means it is this permutation, 2 root notation that we consider. 3 is kept as such, and for this the meaning is 1, 2, 3 in the first row, 1 is taken to 3, 3 is taken to 1, 2 is left as such. Now if you compute this product, you have your 1 taken to 2, 2 taken to 2, so 2, 2 to 1, 1 to 3. So this is what you have, and 3 to 3, 3 to 1. So you have this. So how to represent this in cycle notation? 1 is taken to 1 is taken to 2, so 1 is taken to 2, 2 is taken to 3, 2 is taken to 3, and 3 is taken to 1, so 3 is taken to 1. So this 1, 2, 3 can be written as 1, 2, 1, 3, and that is what is written here. So these are the remarks that will help us in doing any problem or in understanding further theory. Right. So whatever we have said earlier can be explained with this example. Suppose we consider S to be this set and theta to be a permutation in S6, which is given by this. Then we can find the orbit, how to find the orbit of each and every element under theta. Orbit of 1 under theta, by our definition, orbit of S under theta, it is S theta square, and so on. So here we consider the orbit of 1 under theta. So how it is to be written? 1 theta square, and so on. Now if we compute this, 1 we have as that one as such. The meaning of 1 theta is the image of 1 under theta, that is 2. So you have written 2. Next is theta square. So are we to compute our theta square and then only write this? There is no need. Here 1 is taken to 2, by theta square 2 will be taken to 3. So your 1 theta square will be 3 only. 1 is taken to 2 by theta, and 2 is taken to 3 by theta, which means 1 is taken to 3 by theta square. Both mean the same. 1 theta square, it is nothing but 1 theta under theta. You'll have to find out the image. So 1 theta is 2. So you have 2 theta. And this 2 theta is nothing but 3. So you have your 1 theta square, that is the image of 1 under theta square is 3. Now theta cube, the image of 1 under theta cube you want to compute. So it is nothing but 1 theta square, the image of that, and theta. So 1 theta square is 3. So 3 theta we'll have to see. 3 theta is nothing but 1. So you have 1. Again this will be repeated. So you will not be writing if 1 is repeated so many times that the same thing in the set. So only once that you write. So only these are the elements present in the orbit of 1 under theta. And happy to calculate the orbit of 2 under theta or 3 under theta, there is no need, because this being an equivalence class, whenever we have the elements under this equivalence class to be these, there is no need to compute the equivalence class of 2 or 3. That is, orbit of 2 under theta will be same as orbit of 1 under theta, and it will also be same as orbit of 3 under theta. Next, coming to the orbit of 4 under theta, it is 4 theta square, and so on. So 4 is 4 theta power 0, that is identity mapping. So you have that to be 4 only. The image of 4 under theta is 6. And 4 theta square, when we compute, the image of 4 theta square is image of 4 theta under theta. It is the image of 4 theta under theta. So 4 theta is 6. So 6 theta that you have. But 6 theta is nothing but 4. The image of 6 and theta is 4. So you get this to be 4. So that is what is written here. 4, 6, 4 and so on. So you have just 4 and 6. So again this is same as orbit of 6 under theta. There is no need to compute it again. Now for phi theta, because phi is taken to itself, so you consider phi theta square, whatever it is, you will get only phi. So orbit of phi under theta is just singleton phi. Now we consider once we have orbit, it will be denoted with flower braces. The corresponding cycle, it is denoted with ordinary parenthesis, and some book they have with comma separating them, but here we are not using that. This notation only we use for the cycle. So once you determine orbit, you can always have the cycle. So you have this to be 1, 2, 3, 4, 6 and 5. So this orbit of 1, orbit of 4, orbit of 5. So here we can see that they are all disjoint. So the order in which they are written, it need not be, we need not bother about the order in which it is written. Now usually even though we have this to be a cycle of length 1, a cycle of length 1 is not normally mentioned. So you have this theta to be 1, 2, 3, 4, 6. So this again we can write as 1, 2, 1, 3. As explained in one of the remarks, we can always write this in this way. So we have this transposition. See, the number of transposition being odd, this is odd. This is not even, this is an odd number of transpositions. So it is an odd permutation. Odd number of transpositions. So this 1, 2, 3, 4, 6. So 1, 2, 1, 3, 4, 6. Odd number of transpositions. So you have that to be an odd permutation. So if you consider some other example, then in that if you have, say, suppose we consider this 1, 2, 3, 4, 5, 6, 7. We shall see whether at random that we consider. We are not particularly considering any already predetermined permutation. Just like that in S7 we consider one mapping. So suppose I have like this, then we will first write, we want to determine whether it is even or odd. So we consider this, how to write this, 1, 2, 3 disjoint cycle, 1, 2, 3, then 4 taken to 5, taken to 6, 4, 5, 6, 6 taken to 7, 7 taken to 4. So in the first one we have 1, 2, 1, 3. We have 1, 2, 1, 3, and in the second we have 4, 5, 4, 6, 4, 7. So here again odd number of transpositions, so odd permutation only. Odd number of transpositions, so we have this. But there will be cases where you have the permutation being written as even number of transpositions. So we will have them in exercise problems where you will be asked to check whether the given permutation is even or odd. So if we have representation like this, then this is even number of transpositions, so you will conclude that even permutation. And in this case, if you consider this, you have 1 taken to 3, taken to 4, 1, 3, 3, 4, so you have this, and then 2 taken to 6, 6 taken to 2, so this one gets over. And when you have 5, you have 5 taken to 8, taken to 7, 7 taken to 5. So you have this. So here 1, 3, 1, 4. You have 1, 3, 1, 4. and this 126 as such retained, and here you have 58 57. So maybe the examples that whatever we have considered, they are all giving us only odd permutation. You counted number of transpositions being odd. This is an odd permutation, but there are cases where you have the given permutation to be an even permutation by representing the permutation as even number of transpositions. It depends on the permutation that is given to us. So we have this. Now we have in this lemma, every permutation of a finite set is a product of its disjoint cycle. So you consider S to be this, and let sigma belong to Sn. Now we proceed like this. Since 1 belongs to S, by result 2.10.5, which states that you have by that well ordering principle, this one. If S is finite, theta belongs to A of S, then for some k, you have the image of S under theta power k to be S. What is S? S is any arbitrary element in capital S. So we have for 1 we consider that. So since 1 belongs to S, by that result there exists a least positive integer k such that 1 sigma power k is 1. Now we consider the orbit of 1 under sigma. By the definition, it means 1 on sigma and so on. 1 sigma power k minus 1, because 1 sigma power k will give back 1. Now we consider the corresponding cycle, name it as sigma 1. So this sigma 1 is 1 sigma, this cycle. If sigma equals sigma 1, then the lemma follows. Like in this case, we have this. If we consider this permutation, this is my theta say. This is my theta say. So in this case, I have only one. This is the permutation that I have considered, and just one cycle. This is nothing but the orbit of 1 under theta and the corresponding cycle. This is my sigma 1. This is my sigma 1, and this is say sigma. This is say sigma, and this is my sigma 1. So sigma equals sigma 1. So in that case, we have nothing to establish. We have the lemma to be true. If not, there exists one j in S, but j doesn't belong to sigma 1. See, for example, if we consider this one. This is my sigma say. This is my sigma. Now my sigma is this say. Then in that case, we consider the orbit of 1 under sigma. When we compute that, it will be just the set consisting of 1, 2. If you compute it, this is what you get. This is what you get. And the corresponding cycle, when we consider, it will be 1, 2, 3. This cycle 1, 2, 3. So that means in S, this is we are considering in S7. Okay, so even in S5 we can have such examples, but having got this one already, we are dealing with that. So in this, you do have elements in S other than these 3, such that that is not occurring here in sigma 1. So that is what we mean by this statement. So if sigma equals sigma 1, there is no need to go for any other element in S. If not, you can find one j in S, but j doesn't belong to sigma 1. So you have 4 in S. My S in this case will be what? 1 to 7. 1 to 7 that you have. So you have 4 which is not present here, or rather here. So that 1 is present in S but not in sigma 1. So that is what is written here. You have one j in S but j not present in sigma 1. Such that again by the same result, the image of sigma under, the image of j under sigma power L gives us j. Consider your orbit of j under sigma. So that will be this. And let the corresponding cycle be sigma 2. Then sigma 2 will be this. if sigma equals sigma 1, sigma 2. Like in this case we have sigma 2 in this case will be this 4, 5. In this case it will be 4, 5, 6, 7. So my sigma equals sigma 1, sigma 2. Okay, so this will be 4, 5, 6, 7. Because 4 is not present in sigma 1, we consider the orbit of 4 under sigma and the corresponding cycle will be this. So in this case my sigma equals sigma 1 composition sigma 2. If this accounts for my sigma, well, there ends the matter. If not proceeding like this, after a finite number of steps, say m steps, we get as sigma suffix m such that sigma is the product of this, where each sigma I will be disjoint, and that proves our result that every permutation is a product of disjoint cycles. And next we have every permutation is a product of 2 cycles. This one just follows from the previous one because we know already that every cycle is a product of transpositions and every permutation is a product of disjoint cycles. So we have that every permutation to be a product of 2 cycles or transpositions. Next we have the set of all even permutations, which is denoted by an, forms a subgroup of Sn. Now we'll denote by an the set of all even permutations. First we note that identity permutation is always an even permutation, because identity mapping we can always write that wherever you are, whether you are in S3, S5, S4 or S7, whatever may be it, you can write your identity mapping as 1 to 2, 1. So an is non-empty. Next we consider 2 elements sigma and tau in Sn to be the 2 given even permutations. Then both can be expressed as an even number of transpositions, say 2m number and 2n number respectively. So that product sigma composition tau will be expressed as 2n plus 2m times even number of transpositions. So but 2 times n plus m, which is even number, so even number of transpositions. So sigma composition tau will always be again an even permutation whenever sigma and tau are even permutations. So sigma composition tau belongs to an, and hence an forms a subgroup of Sn. Now from this we also note one more thing, that if we have 2 odd permutations, what will be the corresponding composition? It will be even. And when we have 1 odd, 1 even, we will have odd permutation. And just now we had product of 2 even permutation will be even. So how we can have this? 2 odd permutation. One is represented as say 2n plus 1 number of transpositions. The other one is represented as 2m plus 1 number of transpositions. Then the number of transpositions in sigma composition tau, if we consider them to be the 2 permutations, odd permutations to be sigma and tau, sigma composition tau will be an odd permutation. In this case, odd permutations means sigma will have 2n plus 1 number of transpositions. This one will have 2m plus 1 number of transpositions. So the composition will have 2 times n plus m plus 1, that is even number of transposition. Therefore this will be an even permutation. And in the next one, sigma composition tau, one is sigma is odd and tau is even, say. Here both are sigma and tau are odd. Here 1 odd, 1 even. So sigma will be represented as 2n plus 1. Sigma will be represented as 2n plus 1 number of transpositions, and tau will be represented as 2m plus 2m number of transpositions. So total will be 2n plus 2m plus 1, which is 2 into n plus m plus 1, which is an odd number. So odd number of transposition, and therefore this will be an odd permutation. Sigma composition tau, when one is odd, the other one is even, then you have this. Next, as mentioned earlier, 2 even permutation is product of 2 even permutation is even. So one is represented as 2n number, the other one is represented as 2m number of transpositions. So you have even number of transpositions, and therefore it is an even permutation. Now we have the last lemma of the section. Sn has as a normal subgroup of index to the alternating group, namely An, where this An consists of all even permutations. Now for this we shall consider W to be the group of real numbers 1 and minus 1 under multiplication, that is W is this. Now you define psi, a mapping psi from Sn to W by, see we know that in Sn we have odd and even permutations, So you define this mapping in this way. Let all odd permutation go to 1 and all even go to minus 1. So all odd goes to minus 1 and all even goes to plus 1. So like that you have the definition of psi. Odd goes to minus 1, even goes to plus 1. Now this psi is obviously well defined and onto, because all of them are accommodated. They have images and there are only two elements, both of them have pre-images. But it is not one-to-one because they have many images, pre-images. So we cannot say that it is one-to-one, and we don't need it also. Next we have psi to be a homomorphism. So for which we have to show this. You consider two members of this, say sigma and tau in Sn in the domain, and it preserves the operation. That is what, see in the codomain the operation is multiplication of real numbers. So what in the domain the operation is composition. In the domain operation is composition, and in the codomain you have just multiplication of real numbers. So we will discuss cases, because in Sn we have odd, even. So sigma and tau both odd, sigma odd, tau even, and both of them are even. In all the cases this relation will be true. That we will check. If sigma and tau are odd, we know that the resultant is even. So even means image is 1. So you have 1. And that 1 is written as minus 1 into minus 1. But because my sigma is odd, psi of sigma is minus 1. Tau is odd, so psi of tau is minus 1. So this minus 1 is replaced by psi of sigma, and this one is replaced by this. Remember, this dot is multiplication of real numbers, which is commutative. So you may write psi of tau dot psi of sigma also, but that should not be the case, because it preserves the operation. So psi of sigma, psi of tau, it will look nice. Nothing wrong in saying that it is same as this, but that usually we write phi of AB is equal to phi of A into phi of B. Unless otherwise we have the codomain to be the abelian group, we say that it has to be written in that order only. Here it is abelian only. Order is immaterial, but it is customary to write in this way. So we have this. Now let the next case, sigma odd and tau even. Then because it is odd, minus 1, even, plus 1. And composition, 1 odd, 1 even means odd. Odd means image is minus 1. So that minus 1, interpretation only. Minus 1 into 1, minus 1 can be replaced by this, and plus 1 is replaced by psi of tau. And in the same way, the next one. Composition is even, so 1. And that 1 is written as 1 into 1. This is even, so psi of sigma is 1. Again even, tau, so psi of tau is 1. So you have this. Thus in all the cases we have this to be true. So psi is a homomorphism. Because it's a homomorphism, we can talk about the kernel. All those elements which are mapped onto the identity element of the codomain, which is 1. But only the even permutations are taken to 1. So naturally we have kernel psi to be An, that is even permutations. Now we know already that kernel of a homomorphism is always normal in the domain. So kernel psi is normal in Sn, so An is normal in Sn. And in that way we can conclude this using first isomorphism theorem. Since psi from Sn to W is an onto homomorphism with kernel psi, by first isomorphism theorem you have Sn mod an to be isomorphic to W. So both of them are isomorphic, means the number of elements present must be same as the number of elements present here, and the number of elements present here is 2. So, but this is nothing but the number of right cosets of an in Sn, which is nothing but the index of an in Sn. So index of an in Sn being 2, by one of the results in normal subgroups, we conclude that an is normal in Sn. So this is another way of saying that an is normal in Sn, and already here kernel is always normal, so an is normal. In both ways we have the conclusion. But in the statement we need to have the index to be 2. So that is why we are establishing this. So this proves that Sn has a normal subgroup of index 2, the alternating group, namely An, which consists of all even permutations. So later in the next video we will have these problems, exercise problems, finding the orbitant cycles. Suppose we are in S5 or in S6. Okay, then how to find the orbitant cycles already we have seen, and we will see again. And expressing this as product of disjoint cycles. So it has got a method. And computing this, given ABA, how to compute this, which are all even permutations, given the collection of permutations, permutation, whether it's even or not. And then find A such that you have this X and Y are given, you have to find A. And here no permutation such that this holds given X and Y. So all this we will see in the next video. Thank you.